Good afternoon. I'm Faizul Amin. I'm from Intel. I'm going to talk about optimizing XLA CPU with oneDNN. So this is basically going to be a status update of our ongoing effort to optimize XLA for CPU. So here's the agenda. I will briefly talk about what is oneDNN, and then I will describe about a new feature that is available at our fourth generation scalable Xeon processors. There is advanced matrix extension, or what we call it AMX. And then I will talk about how we have been integrating oneDNN library in the XLA, and I will show some preliminary performance results. So having a lot of deep learning frameworks and many kinds of hardware architectures, it is really a complex task, engineering task, to optimize for all the deep learning frameworks. So oneDNN is an open source library that hides this complexity of the hardware architectures by giving some few abstractions and some API to hide this complexity. And most importantly, it is the same API that is used for CPU and GPU. And oneDNN supports x86, ARC64, IBM, OpenPower, and RISC-V, varieties of hardware architecture. And it supports operating systems like Linux, Windows, and macOS. So many of the key operations are supported by oneDNN library, and it supports training with precisions like float 32, B416, float 16, and inference for float 32, B416, float 16, and int8, that is quantized model. And you can see the supported operations grouped into multiple categories. Like you may have data manipulations, like you transpose the data from one permutation to another permutation, or even you convert some data type from another data type. There is some memory bound operations, which typically comes in activation functions or some element as operation. And there are also some compute intensive operations like convolution, matrix multiplication, or RNN. So all the key operations that are found in the deep learning models, that these are supported by oneDNN library. So to give few abstraction from oneDNN library, one is the primitive. Primitive encapsulates a particular computation. It could be, for example, convolution, or it could be matrix multiplication. Even it could be some data manipulations. So it basically stores some parameters like, for example, tensor shapes, or even if we compute some other dependent parameters like what is the cache blocking parameters, for example. So depending on that, it finally generates some GDAT code that are suitable for different architecture. And it also contains some buffers that can store intermediate results. The another abstraction is memory. So memory object encapsulates the allocated memory on some computational device. It also contains some information like data type or data layout or the dimensions of data of the tensor. And next, engine is a abstraction for execution device, for example, CPU or GPU. And then stream is an abstraction for execution context. It gives the, for example, for CPU, it can give an information about how many threads are available for the particular computation. We have recently extended oneDNN library to provide oneDNN graph API. So the goal here is to optimize a group of operations with simpler API. For example, you can see in the top that framework computes a computational graph, and that graph can be translated into another graph, which is called oneDNN graph backend. And by using some graph API, these are converted. And then the graph backend will compute some partitions. So each partition is basically a group of operations that can be optimized, that can have optimized code generation. So you can see in the figure that operation 2 and 4, they are in single partition, while operation 1 and 3, they are in different partitions. So the framework will receive what are the partitions it received from the oneDNN graph backend. And during runtime, each of the partitions will be compiled to generated code. And it will be cached in the compilation cache, and finally it will be executed. And if it is referred in another time, then it will just pick up from the cache without compiling, and it will run it. So it's basically try to simplify the whole graph into the different pieces of compilation unit. So starting from the 4th generation Xeon scalable processors, we have introduced advanced matrix extension, AMX. It has two components. One is a set of tile registers. We have 8 two-dimensional registers, and each of the tile register can be of 1 kilobyte. And each of the tile is basically configurable by some load the tile load instructions. So you can have rows that are smaller than 16, depending on the algorithm, because algorithm can be optimized in a different size of block matrices. So depending on the algorithm, you can reconfigure the tiles to get the best performance. And there are some other the memory related instruction for the tile to load the tile from the memory or to store the tile to the memory, and so on. So basically, a tile or tmul is a set of instructions that multiplies two small matrices. Each of the matrices is contained in some tile, and it only supports only register operation. So we can have before 16 tile matrix multiplication, or we can have integer tile matrix multiplication. So for example, if it is before 16 tile matrix multiplication, then the two tiles are in before 16, and the accumulator will be in float 32. If it is int 8, integer 8-bit integer, then the accumulator is 32-bit, again an integer, but the input tiles are 8-bit integers. So in terms of number of operations per cycle, if we use before 16, then it will be 1024 ops per cycle. If it is inted, then it will be 2048 ops per cycle. So if we compare with the 3rd generation scalable Xeon scalable processor, it is about 8 times, either for before 16 or intake, more ops per cycle. So one important thing is that this AMX and the AVX 512, the computation unit are independent, and they can be overlapped. And as a result, they can go in parallel, and it optimizes the fusion, like if after matrix multiplication, if you have some element-wise operation or any kind of other activation functions that can be fused to the matrix multiplication, for example. So those can be run in parallel, because those will be AVX 512 code. And if the time for the AVX code is smaller than the AMX computation, then basically you are getting free. The post operation of the fusions are getting free. On the other hand, if it is dominated by the AVX 512 code, then it will be the time taken by the AVX 512 code. But most often, we have seen that this small set of post operations or the fusions are getting free. So given that oneDNN library is a high performance library and it hides all the complexity across different hardware architectures, we are integrating the oneDNN library to the XLA. And as you know that the model starts with either TF, TensorFlow, or the JAX expression, and that JAX expression is translated into XLA HLO IR. And there we have introduced several passes. One of the passes for B416. So what we do is we basically allow an operation that is supported by oneDNN library to be in B416. And then we do several pattern matching and do fusions and rewrite to some custom call. For example, if it is dot instruction followed by some other element of operation, we just fuse it into a custom call. And similarly, we have done a layer normalization fusion, which can be found in language models, and also softmax fusions. We are also thinking about fusing multi-head attention MHA using oneDNN graph API. That is work in progress. Besides this optimization, we have also done a few more optimization regarding the tiling of weight metrics that is useful for inference. And we have also done some optimization related to allocating scratch buffer during compilation time. So here I am showing an example of weight tiling during compilation time. So we need weight tiling or the matrix tiling to get the cache reuse, maximize the cache reuse. And there is another reason to do the tiling, because if we want to use the AMX, then the inherent computation is in tiled form. So we need a tiling of the matrices. So here I'm showing some cartoon, like a plane layout, which is basically a row measure here. So oneDNN represents plane layout by a sequence of characters like AB. If it was column measure, it will be BA. So here we can, in the left, we can see a plane layout in row measure form. We want to tile it, and we are tiling the outer dimension A by 8. So the string or the character sequence representation is basically here A, B, 8A. So 8A means the A dimension were tiled, and that becomes the innermost now. So because we know that during inference, the weights are constant, it doesn't change. So we can do during compilation once and then reuse it for the later computations. So for typically the B matrix or weight matrix, here I'm showing. So B matrix is converted to some tiled representation by some custom call. And then that custom call and the A matrix feeds to the MapMal custom call. Since weights are constant, we utilize the constant folding by running the HLO evaluator to convert the B matrix into a tiled matrix representation. And in this way, MapMal can always see the B matrix as in the tile form, and that optimizes. Here I'm going to show some preliminary performance results. This is taken for BART large inference, and we have taken this model from Hugging Face Transformer. We have used Plex version 0.7.2, JAX 0.4.15, and we are using here the throughput mode with base size 32. We have taken the performance number on a GCP cloud with 22 core physical core, that means 44 BART vCPUs. with a 176 gigabyte of memory. So here we are showing performance over multiple sequences like 128, 256, and 384. Each group of sequence length, where the left one is the current XLA without oneDNN, and the middle one is with oneDNN float 32 precision, and the rightmost one is the green one is the before 16 inference. So you can see here that in float 32 precision, oneDNN library is performing twice than the without oneDNN. And when you move to before 16, there is a big jump, and up to 6x improvement you can see with respect to without oneDNN in float 32. So these are very preliminary results where our optimization is still ongoing process. So while we have been doing optimization, we felt that we need some performance profiling. And Intel VTune is a very useful tool to profile and analyze model performance. But when we started using it, we could not use it because the LLVM has Intel JIT event listener, and that JIT event listener was not being compiled with the XLA. So we enabled this compilation, and we have used the Intel JIT event listener to be visible with the VTune profile, because under the hood, VTune uses ITT, which is Intel Instrumentation and Tracing Technology tool. So basically, the Intel JIT listener implements those API from the ITT. So after this fix, we are able to run VTune to get the profile data, and I'm showing here profiles for float 32 and before 16 for 384 sequence length. And the left column, you can see the breakdown of the time taken. So we at the highest level, we have module. A module it could be shared object, or it could be some GTED code. For example, the dynamic code is basically coming from oneDNN library, and it has under the dynamic code we can see 3 tasks. One is the matmal, another is softmax, and another is layer enumeration. And VM Linux is for the systems. And you can see some address. And this address is basically the LLVM generated GTED code. So I think we need to fix it to give some meaningful name, because the address doesn't tell that much. And you can see that when we run this BART model in float 32 precision, almost 90% time is spent on oneDNN library. So that is very much compute intensive. And matmal, you can see that it was taken about 87%. But when you move to before 16, basically the matmal has a lot of speed up. Softmax also got speed up because of the memory bandwidth got reduced. Learnum as well. So on the right hand side, you can see that the proportion has been increased and some proportion is decreased. Overall, we saw that there is a 6x improvement over float 32. So by analyzing this kind of profile, we can point out what is the hotspot, and we try to attempt the future optimizations. So while integrated oneDNN library, we also face some challenges in terms of particularly pattern matching. And we have observed that pattern actually changes even we change the flex version or JAX version. So pattern, we want to say the pattern is not stable. And we also observed that some HLO passes makes the pattern even more complex for the downstream HLO passes. And we have seen that the current passes are kind of sporadic, or it is hard to demarcate or distinguish which of the passes are actually target independent, which are target dependent. So those are mix and match currently. So we feel that it can be reorganized into some modular, like some could be modularized into target dependent, target independent, and some could be as a part of canonicalization. So we feel that that will help us to get better pattern matching for our one integration. And we also think that more technical documentation will be helpful. So here I'm trying to show one snapshot of while we have been doing the softmax fusion. So the leftmost is the graph before a pass, which is called tree reduction. So we can see that the input goes to reduce and then broadcast and then exponential and so and so. But after the tree reduction pass, the right graph is generated, and we can see that the reduce operation has been decomposed into another 3 operations. So we have been struggling actually where to point, where to insert our pass to do the fusion. So for example, here in this case, it is more logical to add our pass just after, just before the tree reduction, because it is simpler. So here are our next steps. We have several pairs. We are waiting to those pairs to be merged for our optimizations, and we'll be adding more pairs with additional optimizations for language models. And as Matt has mentioned, there is a CPU roadmap, so we would like to align with that new roadmap. And eventually, we will be adding more few optimization, for example, for CNN models. And currently, we are targeting inference, but we will be addressing the training perspective as well. And we will also be adding quantization support. And still, we feel that the ITT API for the VTUN profiling is not in good is not a good supportive way. I have seen that the Intel JIT event listener is using very old ITT APIs, so that has to be updated. So we will be trying to improve that profiling with the recent Intel ITT API. Yeah, with that, I would like to ask question and answer.
Hi, thank you very much for the talk. It was very interesting. I have a few questions. The first one, just to double check my understanding, for Torch compile, are you also going to be using HLO-based passes, or how's it going to work? Because there is a Torch compile integration with oneDNN.
Yeah, currently we are relying on the whatever XLA HLO representation there, and we are using that HLO passes. And after that HLO with the HLO fusions or converted into custom calls, then we just we are using this IR emitter, LLVM IR emitter to emit the function calls for the custom call targets. So as long as the Torch XLA transform into this XLA HLO representation, I think it is seamless.
Okay.
Is that the question? That
yes.
Okay.
Sorry, I guess another clarification. So you are emitting calls to MKLDNN API, and then I was kind of wondering, MKLDNN API, I remember they were using their own emitter, XBuick. So are they now using LLVM, or it's still going to MKLDNN JIT, and that one is using XBuick?
Yes, it is. They still JIT code.
Okay. And a follow-up. Which emitter are you using for ARM?
You mean the oneDNN side?
Yeah.
Oh, I am not sure what kind of JITting there is.
Oh, okay. And sorry, one last question. You mentioned like tiled layouts. Those seem to be equivalent to block layouts. That was the
Yes.
original terminology. Thank you.
Yeah, blocked and tiled are synonymous.
Okay.
So
Thank you.
Thank you for the talk. Can you share some thoughts about what you have in your roadmap on quantization? What do you have any?
yeah, actually, I had the same question to the Torch XLA. What is their planning? So currently, what we feel, what we understand is stable HL has only specification, but we haven't seen yet any representation is XLA HLO, because if we have some quantization representation in stable HLO, I think that current XLA HLO will not support that because there is no supportive operation. So we are still trying to figure out whether we take the TensorFlow Lite approach, like we go through completely MLR path, or we wait for some support from the XLA HLO side. So as long as HLO IR has some representation, we will always be able to do some custom form representation.
Sounds good. Well, we'll discuss that in the PyTorch session. So maybe we should
Yeah.
act on that.
Yeah.
Quantization formula.